Welcome back. Today, guys, we are going to continue once again with what we talked about last time, which was figuring out percent composition. Today, what we're going to do is to use that information of percent composition to figure out what is the chemical formula of an unknown substance. So, as always, guys, make sure you take good notes. Write down the example problems we do. That way, you'll have them to help you out in class. So, let's get started. Quick look at what we did last time, right? We talked about percent composition. Problem like this. Find the percent composition of a compound that contains 17.6 grams Fe iron and 10.3 grams of sulfur. So to do this, what we needed to do is divide the total mass by each of them, right? So we found the total mass gave us 27.9 grams. So to find the percent comp, we take for iron, 17.6 grams divided by the total times 100 gave us 63.08% iron. And do the same thing for sulfur, and we end up with 36.92. Add those together and you end up with 100%. So that's what we learned to do on last video. But here's the question. What's the formula for this compound? We know what the percentage is, but we don't know its chemical formula, which is often really useful for us. So let's go ahead and figure out how we can do that today. First thing we're going to talk about is empirical formula. Remember, there's two types of formulas we've talked about, empirical and molecular. The empirical formula, remember, is the formula with the smallest whole number ratio of atoms. So our subscripts are in the lowest ratio. Remember when we did this with ionics, if we had like a 2 and 2 for subscripts, they canceled each other out. If we had a 4 and 2, the 2 canceled a 4 out. Okay, so this is what we've been doing for ionic compounds. We can also do this for covalent compounds. Sometimes we may need the empirical formula. But more likely with empirical formulas, we're going to be using the molecular formula. Okay, here's an example. NaCl has a ratio of 1 sodium to 1 chlorine atom. Okay, magnesium sulfate, 1 Mg, 1 S, 4 oxygen. So that's our lowest whole number ratios that we're talking about. One last one, carbon 2H, 1 carbon, 2 H's, 1 oxygen, 1 to 2 to 1 ratio. Alright, so that's empirical formula. Molecular formula, on the other hand, that's a chemical formula for a molecule. Remember, molecules are things that are held together by covalent bonds. Okay, they are not always going to be the lowest ratio. Okay, those subscripts represent the number of atoms in each element of one molecule. If we're talking moles, though, 1 mole of a molecule, the subscripts represent the number of moles in them. Okay. The important thing about molecular formula is that unlike the empirical, the subscripts do not need to be in the lowest whole number ratio. Okay, that's really important. So example, C2H2, right? We could, if it was an empirical, it'd be CH, but since it's molecular, we don't have to reduce those. Here's another one, glucose, C6H12O6. Here's another one, N2O4. Okay. What we see is that molecular formulas are simply multiples of empirical formulas. So we're multiplying the subscripts in the empirical formula by something to end up with our molecular. Let's take a look at what I mean. So here's CH. The molecular formula could be C2H2. Okay, here's CH2O, excuse me. Its molecular formula is C6H12O6, glucose. NO2 could be N2O4 in molecular form. Here's another one. NO2. Well, if we multiply this by 3 instead of 2, we get N3O6. So two different molecular formulas can have the same empirical formula. Okay, we see that a lot with sugars. Okay, just a little FYI information for you. If there is an unknown compound, if we don't know what its chemical formula is, we can use our knowledge of percent composition and also the mole to determine the correct empirical formula. Then once we know the empirical formula, we can go out and figure out the molecular formula. And that's what we're going to be working on today. Okay, remember, though, that in a correct formula, the subscripts represent the number of moles of each element if we're talking about 1 mole. If we're talking about 1 molecule, it's the number of atoms. But we're talking about moles here, okay? So these subscripts represent what we call a molar ratio. How many atoms of element 1 is there to element 2 or to element 3 and so on. So let's go ahead and talk about and do an example problem on how we can figure out first our empirical formula, then our molecular formula. Okay. So here's what a typical question would look like. What's the empirical formula of a compound that is 67.6 mercury, 10.8% sulfur, and 21.6% oxygen? Okay, well, the thing to remember is no matter how much of this substance we have, whether we have 1 gram, 10 grams, 100 grams, 10,000 grams, the percent does not change. It's always going to be a fixed percentage. Okay, so we can use that to our advantage. If we're not given an amount, let's just assume there's 100 grams. Okay, because what does a percentage mean? It means what out of 100. So if this substance here is 67.6%, that means in 100 grams, 67.6 grams of it is mercury. So it makes it really easy. So if you're not given grams, assume it's 100. If you're given grams, then you're gonna have to figure out, well, what is 67.6% of 32 grams or whatever. But if they don't give you, assume it's 100. Okay, this allows you to change the percentages to grams. Makes it really nice and easy. Okay, the first step for solving for empirical formulas is to figure out how many moles of each substance do I have to start with. Well, let's assume we have 100 grams. That way we can change our percentage to grams, and we can go from there. We said all we simply do is convert grams to moles. So to do mercury, we do that, end up with 0.34 moles mercury. If we do our next one, sulfur, we have 10.8%, which is 10.8 grams, divided by 32.07 gives us 0.34 moles. And then our final one, we have oxygen, 21.6% is 21.6 grams out of 100 grams divided by 16 gives us 1.35. So these represent the moles. And remember, in 1 mole of a substance, the subscripts represent moles. But if you think about a formula, chemical formula, there's never decimals, right? It's always whole numbers. So that's what we have to do in part 2, is to get rid of those whole numbers. And the way we do that is find the molecular ratio. What's the ratio of this one to this one to this one? Well, these two are pretty easy. We can see it's a 1-to-1 ratio. But what about this? Let's take a look. So what we need to do, once we know the moles, we must find whole numbers for the molar ratio. The way you do this is divide each of the moles that we calculate by whatever the smallest mole is. So let's look at this. The smallest is 0.34. So if you take 0.34 mercury divided by 0.34, we end up with 1 mole. If we do the same thing for sulfur, we end up with 1 mole sulfur. If we take 1.35 moles of oxygen divided by 0.34, we end up with 4 moles of oxygen. Now look at this. We have nice whole number ratios there. So we can use those as our subscript. But here's the question is, which order do these go in? Is it mercury first? Is it sulfur? Is it oxygen? Well, we have to go back to what we talked about first semester. Okay. Well, we got 3 substances. Okay, there's no carbon in them, so it must be a polyatomic. It must be a polyatomic, it must be ion. So that means positive plus negative. Well, we know our positive one is mercury. Okay. So positive goes first, the mercury. And then you have 2 nonmetals, so they must somehow come together to form a polyatomic. There is 1 sulfur, 4 oxygen. Look at your poly sheet. What ratio is that? Or what polyatomic is it? Sulfate. Okay, so we find one that fits. We end up with HgSO4. Okay, so pretty easy. First, find how many moles of each substance, and then find your molar ratio by dividing each mole by whatever the smallest mole that you found. That gives your ratio, and then put them together in the correct order. So if you're not sure the correct order, go back and check out your notes on bonding. Okay, let's try a practice problem. I'm going to give you 2 parts of this, and we're going to focus on part 1, then I'll show you part 2. So here we go. A compound contains 54.4% carbon, 13.6% hydrogen, and 31.8% nitrogen. The molecular mass of the mole of 1 mole of the substance is 88.18 grams. So some new information there. 2 things I want you to do. Calculate the empirical formula, and then also you're going to calculate the molecular formula. But for doing the empirical formula, ignore all this second part stuff. That's going to help us when we calculate the molecular formula. So here we go again. We're in percentages, so assume they're 100. Okay? Assume we have 100 grams. Go ahead, pause the video here, work this one out on your own, then come back and check your work. See how you did on part 1 of this. Okay, hopefully you have done this on your own. If not, stop cheating. Pause me now, go back, do this problem. You're not going to learn unless you do it on your own. Okay, so first thing we have to do is convert each substance to grams, or excuse me, each gram to moles. Okay, we do this simple ping pong. Okay, what we want stays on top, what we want to get rid of goes on the bottom, so moles on top, grams on bottom. Okay, and we end up with this many moles. Now if I look here, my lowest one is 2.27, so I'm going to divide each number by 2.27, which gives me a ratio of 2 carbons, 6 hydrogen, 1 nitrogen. Okay, I have 3 substances, okay, so most likely it's one of 2 things. Okay, it's either an ionic compound or a molecular organic. Okay, well, first of all, I know it's asking for the molecular formula, so that tells me it has to be a covalent and not ionic. Okay, so it has to fit in one of 2 categories. Binary compound, well, binary means 2, and there was carbon, hydrogen, and oxygen, so that can't be this one. So it has to be an organic. Okay, well, what order do our organics go together? Think of good one to think of is glucose, C6H12O6. Okay, keep that in your mind. Well, we always put the carbon first. Okay, then we write the hydrogen, then we write whatever else is left. In this case, it's going to be oxygen. So if we take those ratios we just figured out, we end up with C2H6N. All right, so that is our ratio there. Okay, now we need to go to part 2, and that's figuring out the molecular formula. Okay, here was what it says. Now we need to calculate the molecular formula part of this. The second part, this right here. Take in the second part of information they gave us. Okay, once we know the empirical formula, the molecular formula can be determined if the molar mass of the compound is known. Well, they gave us the molar mass of the compound. So remember, the molecular formula is just a multiple of the empirical. So we're going to multiply the subscripts in the empirical by some value to get our molecular. So we calculate the mass of the empirical formula. We know its formula, okay, but now we need to calculate its atomic weight, okay, and then divide the molar mass of the compound by the molar mass empirical formula, and that will give us our ratio that we're going to multiply our subscripts by. Now it's a mouthful, but it's pretty easy. Okay, and then finally we multiply all the atoms, the subscripts of the atoms in the empirical formula by this ratio to get the molecular formula. So let's go ahead and look at what this would look like. Okay, so calculate the mass of 1 mole of empirical formula. There was our empirical formula. So we got to have carbon, which is 12.01, I think, multiplied by 2. H is 1.01, okay? And then nitrogen, I think, is 14.01. When we do this, we come up with a atomic weight of 44.09 grams for 1 mole of the empirical formula. The problem told us that 1 mole of the molecular formula weighed 88.18 grams. Well, to figure out what our multiplier is, we just take the mass of the molecular formula, okay, divide it by the mass of the empirical formula, and get a multiplier of 2. Okay, 88.18 divided by 44.09 gives us 2. This is our multiplier. We're going to take this 2 and multiply each of the subscripts in here by that to get our molecular formula. Okay, so when we do that, we end up with C4H12N2, and that's our molecular formula. So pretty easy. Okay, we do need to know the molecular mass or the molar mass of the molecular formula to be able to do this. Okay, guys, just a quick review of how to do the empirical formulas. You may want to copy this down. It'll help you to remember. Okay, first, assume there's 100 grams of the sample. Second, convert all those percentages to a mass in grams if we are assuming 100. That way, percentage just put grams. Okay, so 21% becomes 21 grams. 9% becomes 9 grams. Seriously. Then you're going to use the atomic weights to calculate the moles of each element. Okay, so once you know the moles, you're going to divide the moles of each element by whatever the smallest is. Okay, and this will give us our molar ratio. Hopefully, that molar ratio comes back as whole numbers. Okay, nice, neat whole numbers. And we can just put them into our formula following our rules for naming and so on. Now, the problem comes in is if when you divide by the lowest, you don't get these nice whole numbers. Okay, if you don't, you're going to need to manipulate them a little bit farther. Okay, so if it's too far around, if it's more than like 2.1 or 6.9, we can easily round them. Go ahead and do that. Okay, but if it's like 1.25, 1.5, 1.75, 1.33, what you're going to have to do is multiply those by some factor to get a whole number. So if you have 1.5, well, if I multiply that by 2, it's going to give me 3. Then I have to multiply all the others by 2 as well. If it's 1.33 and multiply it by 3, that gives me a whole number ratio there. Then I got to multiply all the other ones by 3. We'll get more practice on this in class. Alright guys, then once you have the empirical formula, you find out the molar mass of the molecular compound, divide that by your molar mass of your empirical. That gives you your multiplication ratio, and you can multiply all the subscripts in your empirical by that multiplier and figure out your molecular mass. Okay, so now in this episode we learned how to write the molecular and empirical formula. Actually, we learned the empirical formula first, then molecular formula from the percent composition. So, tough problem might first find out the empirical formula, first find out the percent comp, then find out the empirical, then find out the molecular. Okay, if you're not understanding this, get ahead of the game. Stop in and see me, and I will be glad to help. Otherwise, make sure you got all those problems copied down. If you missed some of them, rewind, copy them down. So when we come to class and we do practice on this, you will be able to look at your notes rather than come up and ask me without looking at your notes. So make sure you have those down, guys. And if you have questions, please come see me. Otherwise, I will see you in class. Take care until then.